Hello and welcome to One Electron Universe. In the past two videos, we saw how to convert alternating current to direct current. In this video, we are going to build a circuit to do blinky lights, and to do that, we will figure out how to convert DC to a pulsating DC. Do watch till the end of this episode if you would want to know why I chose to build this circuit. Before we begin, a small note on circuit design. Designing circuits is easy and difficult at the same time. It is easy because most of the design problems we encounter have been studied before, and it is relatively easy to find many circuit designs on the internet to solve the problem. However, it is difficult because not all designs can be replicated or used as is. This could be because of the different specifications needed for your requirements, or the fact that components vary widely in their real-life performance. A few percent variance in the advertised value of a component can have a drastic different outcome. So, even if you were to replicate the design you find online, you may not get the exact same outcome. And it is not just about the components of the circuit. The availability of components and tools that you use, the breadboard, the connecting wires, the quality of soldering, the power source, the ambient temperature of the environment, and many such parameters impact the outcome of the design. You have to design circuits to be tolerant. One example of such a circuit is the LED driver we examined in the previous videos. It can take a wide range of input, anywhere from 175 volts AC to 265 volts AC, and convert it to a fairly stable output of 250 milliamperes DC to drive the LEDs. Let's go through a simple design process to build our circuit. How do I design a circuit? Let's look at the steps that I normally follow when I'm designing a circuit. The first step is to identify the characteristics of the circuit. Is the output some kind of a visible indication like an LED? Is the output, let's say, a sound output? Let's say you're making an amplifier, so you want the sound to be loud enough. You want to amplify a certain sound. The output could be physical, moving a robotic arm, for example. Or the output could simply be data sent out to a larger system somewhere in an IoT scenario, for example. What does the input look like? What is the input to the circuit? Is the input a user activity? Is the input an environmental factor like temperature? Is the input an optical thing, a visible thing like light sensing device? What are the power inputs to this? Are you going to take the power from a battery? Are you going to take the power from the mains? Now, these two will more or less define what you need to do with the circuit. However, there are many other considerations that you will need to do to have a successful circuit. Things like cost, things like availability of components, things like power consumption and the efficiency, and the form factor of the circuit. Is a breadboard good enough? Breadboard might not be a good solution for a circuit that's going to be used for a long term. It cannot be a permanent solution, for example. Same thing with power consumption and efficiency. What kind of cooling do you require for the circuit if it's going to be used for longer terms? What kind of components are you going to use? Are you okay soldering surface mount devices? Do you need through-hole technology components? There are many such considerations which will come into effect when you're designing a circuit. These three are the most common ones which I use when I design my circuits. Once you have identified the characteristics of the circuit, and you need to document all of this, right? Because it's very easy to forget something while you're looking for components and stuff. So once you've documented all this, then you need to identify the type of circuit that will help you achieve this goal. Normally, the problem that you're trying to solve, somebody would have already studied and solved it in the past, and you might just have to look up the internet, you might have to look up textbooks, you might have to look up documents. In fact, if you look at data sheets of many electronic components, they do normally have circuit examples as to how to use those components. There are tools available which will help you design and build a particular circuit. Once you've done this, you need to do the maths. You need to calculate the individual component values of the circuit so that you get the outcome that you're looking for. Again, the formulas may already be available in textbooks, on the internet, in data sheets, Optionally, once you have done all this, you may want to simulate the circuit before you actually build it. Now again, when you are doing things for fun, maybe not, you may not want to do it, but definitely when you're trying to do this professionally, you definitely need to simulate and see if your maths, your calculations, and your circuit design is correct before you actually go and implement it. This is also about cost, right? You might end up procuring wrong components, building a circuit that doesn't work. Simulating it beforehand always helps. And then finally build and test the circuits. So these are the 5 simple straightforward steps that I normally follow when I design circuits. However, the most important point in doing all this is don't get electrocuted. Now electronic circuits normally use low voltages and low currents, so this may not always be the case. But remember, you do end up using mains power to power your circuits, like we will do today to power the breadboard. So you need to be very careful when you're dealing with these kind of power sources. And of course, don't burn the house down. Now, electrical shorts are a leading cause of fires worldwide. So you should definitely be very careful and take all safety precautions to make sure that you are avoiding shorts in your circuit. Let's look at the characteristics of the circuit that we're trying to build today. What does our output look like? Of course, what we want is blinky lights, right? We want the lights to go on and off at a certain period of time. There are many ways of doing this. For example, if you look at it, here there are 4 different waveforms which can give us a similar effect, right? The top half will switch on the LED, and the bottom half of each of these waves will switch it off. Now what we need is a LED which goes on and off for equal amount of time, and it's fairly stable. So we are going for a square wave. Now I want the peak output to be less than or equal to 3 volts. Why is this important? Now that's important because I'm trying to do something with this circuit, which I will cover at the end of the video. So let's assume that we need an outcome which is less than 3 volts. And we want to drive an LED with this, right? So we obviously want, and we want this to be human perceptible. So what it means is, if the LED is blinking too fast, I will not be able to make out that it's blinking. And if it is blinking too slow, again, I might not be able to make out that it's blinking. I might think it's off or it's on, depending on at what time I look at the circuit, right? So we arbitrarily choose the frequency between 1 and 10 Hertz. What does the input look like? In our case, it's very straightforward. I'm trying to run this circuit out of a DC battery, so it would either be a DC, so the idea is we will assume that we already have a DC output available. So it could be run off battery, it could be run off a breadboard power source, or you could use a LiPo battery or a AAA battery, or whichever kind of batteries you need. But the idea is that the input voltage will be somewhere in the range of 3 to 3.7 volts, not very high in this. This also has the added advantage that we don't have to do anything special to make sure that the outcome is close to 3 volts, right? Because there will be some losses in the circuit and the outcome will be very close, much closer to the input than anything. So now that we have the characteristics decided, and of course the other characteristics are very simple, straightforward, we will go with whatever components are available. So what all circuits can help us do this? Now interestingly, blinking lights is more or less the hello world of the electronics world, right? So when you search for how do I create blinking lights, you will see hundreds of circuits and tutorials on how to do it using an Arduino, using a Raspberry Pi, using any of the 32-bit microprocessors, ARM microprocessors out there, even a microbit. And that is more about writing software than anything else. Now, you will find circuits which use the any 555 timer or any other timer for that matter, which will again help you create a square wave and blinking lights. But then point is, where's the fun in all of this? Because none of this actually helps us understand how the various electronic components actually work. Or what we are looking for is an astable multivibrator, also known as an astable oscillator. This is what the circuit looks like. As you can see, it looks a bit complex, but it's not. It's pretty straightforward, and if you notice, it's a very symmetrical circuit. The left half and the right half look very similar. This circuit basically leverages 2 capabilities. One, the switching action of the transistors Q1 and Q2. So Q1 and Q2 in this case are NPN transistors. What you also need is some way of switching this on and off on a periodic basis, and that's where we leverage the charging time for a capacitor, or the amount of time that a capacitor takes to charge up. This is normally an exponential curve, and this will in fact a logarithmic curve, in fact a reverse exponential curve, and this will become important later on when we see the formulas. But so the idea is that we are going to take the ramp up voltage of a capacitor and the switching action of a transistor to achieve the outcome that we desire. As I said earlier, the resistance and the capacitance, the RC, this is basically an RC circuit, which R3 is C2 or R2 and C1 form. So the rate of switching is directly proportional to the value of the resistance R2 and R3 and the value of capacitance C1 and C2. In fact, the time taken for a single on and off cycle is T, which is equal to log of 2, natural log of 2, multiplied by R2C1 plus R3C2. Now to simplify things, we can have R2 is equal to R3 and C1 is equal to C2. The added advantage here is that when R2 and R3 and C1 and C2 are same, we get a 50% duty cycle square wave, which basically means the circuit will be on and off for the equal amount of time. The time formula simplifies and it becomes 1.386 times R times C. That's it. It's as simple as that. And the frequency, of course, is the reciprocal of the time taken. So that's 1 upon 1.386 multiplied by R multiplied by C. So now let's calculate the values of each of the components. As I said, we will go with availability. I have a 10 microfarad capacitor, electrolytic capacitor available, which can tolerate up to 25 volts, which I think should be good enough for the circuit. We should have a safe margin on the components that we use. Earlier, we decided that we wanted the frequency between 1 to 10 hertz. So if the frequency is 1 hertz, the value of R comes out to be 72 kilohertz. If the frequency is 10 hertz, the value of R effectively is 1/10, which is 7.2 kilohertz. Again, going by availability, I do have two 100 kilo ohm resistors, so we can put them in parallel and make a 50 kilo ohm resistor, which will then give us an effective frequency of 1.5 hertz, so which basically means the LED will blink 3 times in 2 seconds, which should be very easily visible for the human eye. So this is good. And so this gives us the values for R2, R3, C1 and C2. Now what about R1 and R4? Now R1 and R4 also play a very important role in the circuit. R1 and R4 are called the current limiting resistors. They limit the amount of current that flows through Q1 and Q2, right? And again, we don't want to blow off any components. So we need to choose R1 and R4 so that the current flowing through Q1 and Q2 is always less than the tolerable max limit that they have. Now, if you look up the data sheet for Q1 and Q2, these are, as I said, 2N2222 transistors. It's around 600 milliamperes. So we should normally take 600 milliamperes current and find the minimum resistance that's required for the current to be below this. That's not what we are going to do. Why? Because we are going to put LEDs in series with R1 and R4. So not only should we look at the current limit for transistors Q1 and Q2, we should also look at the current limit for the LEDs. And the current limit for the LEDs is much lower than for this transistor. So we will take 20 milliamperes, which is the current limit for the LED, to do our calculation. And calculating, so our input voltage is 3.3 volts. So calculating that, we get R is equal to 165 ohms. So we can have R1 and R4 should at least be 165 ohms or more. This is what the final circuit is going to look like. Now that we kind of have our components, let's go over to false start and simulate the circuit. And while simulating the circuit, I will also explain how exactly it works and how we get the switching action. Before we can simulate our circuit, I just wanted to show you something which I have mentioned in the past. It works in practice. Does it work in theory? And this is an example of it. Now in this circuit, if you notice, the left and the right, they're very symmetrical. And because the simulator is using an idealistic idea of how an ideal component should work, you can see that there is absolutely no oscillations. It's not oscillating at all. And that's because it assumes that a 330 ohm resistor, both the 330 ohm resistors are equally identical, and which basically means an equal amount of current is flowing in both the sides and there is no switching action whatsoever. As you can see, there's no current flow through the capacitors. They are not getting charged at all. Now, this, as I said, this is not a problem with all simulators. Some simulators do it. Some simulators basically do assume a real world behavior of the components. In real life it works because not all components have the exact same advertised values, right? Some components will be slightly lower or higher. In fact, most electronic components will have a tolerance advertised along with the values. What we of course will do is, to avoid this, make our oscillators R1 and R4 slightly different, right? So here instead of having 500 ohms on both sides, this is 510 and this is 490. This is again within the tolerance limit. In fact, this is 2% off, right? So we're assuming that R1 is 2% above value and R4 is 2% below value, right? And again, in practice, you won't have to do this. In practice, you will, as you saw in the circuit, earlier circuit, the physical circuit that we saw, both resistors were 500 ohms, and because of the minute difference, because of the differences in their actual values, the oscillations will happen. So now let's look at this circuit. And I have set the simulation speed low so that we can actually understand what's going on in the circuit. Now, before I switch this on, before we start this off, right? So let's see. The input is 3.3 volts. R1 and R4 are effectively 500 ohms. R2 and R3 are 50K as we calculated. C1 and C2 are 10 microfarad electrolytic capacitors. Now, the most interesting thing, or the most important thing to know when we try to understand the circuit, is the voltage levels across the capacitors, right? So this is the left side of C1, this is the right side of C1, and you can see that right now, I have stopped the circuit, but right now, when Q2 is on, right? Q2 is on. Now, what you can see here down in the scopes, this, as you can see, is voltage across the collector and emitter of Q1, and this is voltage across the collector and emitter of Q2. Now, because Q2 is on, you can see that the voltage across the collector and emitter, the voltage drop across collector emitter is 112 millivolts, right? A very low value because it's right now conducting and the resistance is very, very low. And that is because the right side of C1 is at 625 millivolts. That's 0.625 volts, which is the gate voltage to switch on the transistor, right? For Q1, the left side of C2 is at minus 691 millivolts, so which is basically switched off this transistor Q1. Now, because transistor Q1 is switched off, more or less all the voltage, 3.3 voltage, is applied here on the left side of C1. And now again, as I said, this is probably the most important part of the circuit to understand. The left side of C1 is at 2.1 volts. The right side of C1 is at 0.6 volts, which basically means the voltage across C1 is 0.6 minus 2.1, so that is 1.5 volts. Now, why is this important? This is important because when Q1 switches on, this voltage here will effectively become zero. It will be whatever this voltage is, which is 116 millivolts, right? 112, 116 millivolts. And when that happens, the right side of C1 will effectively become negative 1.5 volts. Now we will simulate the circuit, and I'm going to simulate it at a very slow speed. Now, just quickly for the basics, the yellow dots that you see, that's the conventional current that's flowing. Now, as we discussed earlier, Q2 is on right now, it's conducting, and that's why you will see that the LED on the right hand side is glowing. And because it's glowing, and unfortunately it's not, now you can see, and because Q2 is conducting right now, you will notice that the capacitor C2 is being charged, and the voltage on the left hand side of C2 is slowly decreasing, right? It's negative, so as the numerical value decreases, it means it's being charged, right? Now, when this voltage reaches 625 millivolts, and it's some 620, 625 millivolts, this will effectively switch on Q1. So right now, as you notice here, Q1, if you look at the scope below, Q1 is at 2.1 volts. That's because Q1 is off. So the collector of Q1 is at 2.167 volts. And here the collector of Q2 is at 119 millivolts because it's conducting right now. right? So if you notice that, again, I'm just repeating, but C2 is being charged via Q2 right now. And this is why you will also realize why this resistor, which is R3, and C2 are important for the switching times, because the amount of time taken for C2 to be charged to 0.65 millivolts or 0.62 millivolts, whatever is the switching value for Q1 for the base emitter voltage, will decide the time taken by the circuit to switch on and switch off. So LED, right now the right LED is on, the left LED is off, and in a few seconds, and I will increase the speed, in a few seconds, okay, mind you, the simulation is really slow, right? As you can see, each time slice is only 200 milliseconds or so. So right now the simulation is actually happening at a very slow speed. Okay, let me speed up the simulation so we might be able to see some. Yeah, we're getting very close, not yet though. Okay, so now it's gone into the positive territory, and okay, now let me slow it down a bit. Now you can see here, the left side, the C1, the right side of C1 is fairly stable at 625 millivolts. The left side of C2 is now getting charged, and it's getting closer to the 0.625 voltage. That is what we need to switch on Q1. And as you can see, the current has now started flowing through Q1. Obviously, there's not a direct switch off, but the moment that happened, and let me stop this, the moment Q1 switched on, the collector of Q1 was pulled down to effectively 0 volts. Here you can see 39 millivolts, which basically made the right side of C1 to be at minus 1.5 volts. And this switches off the Q2 transistor. And because now Q2 is switched off, the voltage at the collector of Q2 is rising. It's now 1.089 volts. Of course, this all started off because the left of C2, sorry, the left of C2 charged to 640 millivolts, right? So now C1 is conducting, Q1 is conducting, and Q2 is off. And you can see that the LED here is slowly going off. Let me just run this, and you will notice that the switching action, if you look at the scope below, the switching action has happened. Q1 has suddenly switched on. You can see a sharp fall there, and Q2 is slowly switching off, right? And in fact, by now, I think the switch off and switch on action is more or less complete. And if you notice, this action takes within a few milliseconds. Yeah, it's a very quick action. So now C1 will get charged via the R2 resistor, the 50K resistor, when the right hand side of C1 will charge up to 0.6 volts. Q2 will now switch on, Q1 will switch off, and the right LED will switch on and the left LED will switch off. So this is what gives us our blinking effect of LEDs. Hope this helped you understand the circuit. Now we can go back to our presentation. So this is what our final circuit looked like, and this is what helped us achieve the blinking lights. Now we have our blinking lights, but how can we check the square wave? That's where this microbit comes in. In the next video, we'll be using the analog to digital converter of this microbit to create a simple oscilloscope. If you enjoyed this video, and if you would like to see how to build an oscilloscope out of this microbit, please do watch the next video. This is the One Electron Universe. Thank you and take care. Bye.